Thank you. Thank you, Claudia, David, everyone, for the opportunity to be here today with you. Um, I realize I'm one of three people standing between this hypoglycemic crowd and lunch. I'll try to be brief and high level. I'm an assistant professor here at Mount Sinai in the AI department and in the Department of Medicine, as well as CTO of Oatmeal Health. I want to talk to you about how deep learning can augment the diagnosis of nodules or the risk estimation of nodules identified on low-dose CT. The problem that we're here to solve is that while LungRADS is an excellent classifier of risk or estimator of risk, remains imperfect, and we're all looking to find those fail cases and improve upon that diagnostic algorithm. Currently, just citing a paper from last year, estimates the sensitivity, taking the threshold between 3 and 4A at 91%, 82% specificity. So about 9% of nodules missed, 18% misclassified. Those are the nodules we're trying to reclassify, and there's room for improvement here. The goal here is not just to improve the diagnostic accuracy of nodules, but as we trend towards a more perfect estimator, to enable the expansion of the indication for lung cancer screening. Now, not to take away from feature engineering and the development of rule-based algorithms, I think the work that goes into iterating, identifying the fail cases of LungRADS and continuously iterating on that model is truly essential. Here I propose kind of going in a 90-degree direction to find entirely new features. The hypothesis of applying machine learning to diagnosis is predicated really on kind of two premises. One, that given enough data to train on, that we'll find features that we just didn't think of, or we haven't, that the deliberate process of feature engineering would eventually find that just hasn't yet. I think the more interesting hypothesis is that there are just features that are uninterpretable or imperceptible, and that by using deep learning trained on the voxels themselves, we can find features that might eventually factor into the next generation of a decision tree algorithm, such as LungRADS. Turn your attention to a couple of the existing models I consider to be of some of the most cutting edge in industry currently and in academia. The Sybil model has been touched upon previously today, has an AURC of about 0.93 to 0.94 on a held out set of the NLST data set. Of course, Optelum's algorithm that was cleared a few years ago for the risk stratification of incidental nodules. To posit that some of the limitations of where we are today in machine learning for risk stratification of lung nodules are one, focus on the nodule as a standalone, or focus on the nodule specifically without considering the context of the scan as a whole, limited integration of metadata, limited integration of the brilliantly engineered features that we have identified over time are predictive of lung cancer, and the lack of temporal modeling. And so at Oatmeal Health, we developed a computer-aided diagnosis tool for the estimation of malignancy risk from nodules identified on low-dose CT. And some of our design philosophy ideas to kind of address some of the problems that we saw in existing methodology were, one, that both the nodule and the scan as a whole contribute information. Focusing purely on the model and ignoring the scan might lose essential information. And that might be as simple as, the identification of emphysema on the scan, perhaps risk modulating probability of lung cancer. We don't know. There's the underlying hypothesis that modeling the scan would improve performance. Two, incorporating metadata that we saw to be highly predictive, and it isn't and aren't routinely included in machine learning algorithms. demographics, smoking history, the scanner used, software used, the kernel used. Three, using high quality features such as nodule size, morphology, classification as solid, subsolid, etc. Features that we've identified over years of ituration to be highly predictive of malignancy. And four, and I believe most importantly, the explicit temporal modeling of nodule evolution, which we do in LungRADS, but deep learning perhaps could add another dimension to the explicit modeling of nodule evolution over time. I'm going to, without getting too deep into all of our studies, just present some of our early kind of seminal results, just performance on the NLST data set, comparing to a cohort annotated by chest radiologists. We see LungAI, this deep learning algorithm, to improve upon the pure LungRADS classifications without, of course, a clinician interpreting, from 0.88 to 0.96. How this plays out, I think, will be curious in clinic, but taking the sensitivity and specificity thresholds that LungRADS achieved, 91, 82 in this cohort in which we studied, this held out cohort of NLST, we take if we threshold to achieve 82% sensitivity or specificity, we can boost sensitivity to 94. We threshold to achieve 91% sensitivity, we can boost specificity to 87. And conversations I've had in the field, a lot of different opinions on whether thresholds of a continuous score such as this should be geared towards improving sensitivity, improving specificity, or leaving it for the radiologist's determination. And I'm excited to see how algorithms like this play out in factoring into the next generation of decision making. I think I find this to be quite interesting. This is essentially taking all the different hypotheses away one by one, ablating the hypothesis that embedding the scan is important, the nodule is important, that module directly modeling the metadata, and most importantly, taking a prior scan into information into account, directly testing the hypothesis of whether that actually makes a difference. We see this is a very limited cohort, mind you, that a couple of these do pan out, at least taking away nodule embedding information as well as nodule metadata information significantly reduces performance. Taking away the prior scan, we don't achieve the 0.05 mark, but again, it's very limited data sets. We intend to validate externally on a much larger set soon, so stay tuned. So just in summary, I think what we're positing here is that the use of deep learning to incorporate existing high quality features and then produce new ones to identify things that we may not be able to see with the human eye, to be able to predict development of lung cancer, may eventually augment our diagnostic algorithm for lung nodules on low-dose CT, both reducing unnecessary follow-up and eventually, hopefully, expanding screening eligibility. Thank you guys for taking the time to listen to me today.